Hotkeys in a cache. This is one of the most useful topics in system design, and almost nobody meets it until it happens to them. Let us understand it properly.
It is 2 in the morning. You run a ticket site. A big concert has just gone on sale. Checkout starts timing out. Users see spinning wheels. Orders fail. You open the cache dashboard first because the cache sits in front of everything. A cache is a group of machines that keep answers in memory, so the database does not have to work them out again. You have 10 of them. Memory is 30% used. Nothing is being thrown away. Average processor load across all 10 machines, 11%. 11%. The cluster is almost asleep, so the cache is healthy, and the problem must be somewhere else. It is not somewhere else. One of those 10 machines is at 96%. The other 9 are at 1%. The average hit it completely. And here is the part that surprises people. If you add an 11th machine right now, that one machine stays at 96%. You cannot buy your way out of this. Let me show you why.
The subject today is how a distributed cache decides which machine holds a key. That sounds like a small detail. It is the whole story. We will cover 4 things. First, how a key is assigned to a machine. A hash of the key text picks it, and the same key always lands on the same machine. Second, why that is normally fine. Random keys really do spread almost perfectly. Third, what a hotkey is. One key takes most of the reads, so one machine takes all of them. Fourth, what you can actually do about it and what each fix costs you. 2 things this is not. It is not eviction, which is running out of room. It is not invalidation, which is keeping cache data correct. This is running out of one machine while 9 sit idle. It bites during flash sales and ticket drops, when a post goes viral, and on any homepage row that every single request touches. Here is the picture I want in your head. A post office with 10 counters. There is a rule painted on the wall. The first letter of your surname decides your counter. A to C goes to counter 1. D to F goes to counter 2, and so on down the row. On an ordinary morning, this works beautifully. Surnames are mixed, so people spread out by themselves, and every counter has 2 or 3 people waiting. Nobody waits long. Now the whole town football club arrives to register. Every one of them is called Mueller. The rule sends every single Mueller to the same counter. That counter has 300 people in front of it. The other 9 counters are empty, and the clerks there are leaning on the desk with nothing to do. Now open an 11th counter. Nothing changes. The rule still sends every Mueller to one window. That is a hotkey. The rule is not broken. The rule is working exactly as it was designed to work. Let us look at the rule itself, because it is smaller than you think. This is a cache client. Nodes is a list of 10 cache machines. The function called node4 takes a key and returns the machine that holds it. First line, take the key text and run it through crc32. That gives you one number. Second line, take that number modulo 10. That picks the machine. That is the whole thing. There is no lookup. There is no directory service. There is no coordinator. Every application server in your fleet runs these same 2 lines and gets the same answer without talking to anybody. And the spread really is good. I ran 1 million keys through it across 10 machines. The busiest machine ended up with 100,360 keys. The quietest got 99,645. That is about 1/3 of 1% away from the average. So this property is why the design scales. It is also exactly why a hot key cannot be fixed by adding machines. Here's that picture, drawn. 10 machines, 21,000 reads a second, coming from your application servers on the left. The application servers pick the machine themselves, using the 2 lines we just read. The database is underneath, and it is only touched when the cache does not have the answer. Every machine holds 1/10 of the keys. Every machine uses 1/10 of the memory. Every machine answers 1/10 of the reads, so every one of them sits at 10.5%. This is the diagram everybody carries in their head, and for keys that are read at random, it is completely correct. But look at the assumption hiding inside it. That picture assumes the reads are spread out the same way the keys are. They are not. And the reason is very simple. A link exists. Your million keys really are spread evenly. That part is true. But nobody reads 1 million keys at random. People read what is linked to. One concert goes on the homepage. One post gets shared.
One product goes on sale at 9 in the morning, so the keys stay spread out, and the reads all pile on to one of them. And because hashing is deterministic, the thing we just called a feature, every single one of those reads goes to the same machine. There is no load balancer in between. There is nothing there to spread them. The key decides the machine, and it is always the same key.
Let us put real numbers on the same diagram. 10 machines, unchanged. 21,000 reads a second in total, unchanged. But 19,000 of those reads are for one key, the event page for that concert. That key hashes to machine 3 every time. So machine 3 now handles 19,200 reads a second. If a machine saturates at 20,000, that is 96%. Every other machine handles 200 reads a second, 1%. And the cluster average is still 10.5%. 89.5% of the cache you are paying for is doing nothing at all. Look at the pipe going into machine 3. It is doing 96 times the work of a typical machine. Not 96% more, 96 times.
3 numbers, and they are all true at the same moment. 96%, the processor load on machine 3. 10.5%, the average across the cluster, which is the number your dashboard shows you by default. 800, the reads per second of headroom machine 3 has left before it starts refusing work. At 19,000 reads a second, one more share of that concert link uses that up. This is why the failure is so hard to see. The number that is wrong is not on your screen, and the number on your screen is not wrong.
So the obvious move is to add machines. I measured that too. At 10 machines, the hot one sits at 96.0%. At 15 machines, 95.66. At 20 machines, 95.5. You doubled the cluster. You doubled the bill. The hot machine came down by half of 1 percentage point. Meanwhile, the cluster average fell from 10.5% to 5.25%. So your dashboard now looks twice as healthy while nothing has been fixed. And the tiny drop you did get is not the hotkey being shared out. It is only the small amount of ordinary traffic that moved off that machine. The 19,000 did not move at all because the key still hashes to exactly one place. Here is the sentence to remember from this whole video. Sharding distributes keys. It does not distribute traffic. On the left are the things sharding genuinely balances: how many keys each machine holds, how much memory each machine uses, and which machine owns a key after one of them dies. Adding machines divides all 3 of those. On the right are the things it never touches: reads per second, processor time on one core, and network bytes leaving one machine. Adding machines divides none of those. A single key is a single machine, always, because the mapping is a function of the key text and nothing else. At this point, somebody always says, use consistent hashing with virtual nodes. Let us actually test that, because this is the sharpest distinction in the topic. Here is a hash ring. Each machine gets V points placed around the ring. A key goes to the first point clockwise from its own hash. Now look at the table. Plain modulo from earlier gives a key spread of about 1/3 of 1%. A ring with 1 point per machine is terrible. The busiest machine held 339,000 keys, and the quietest held 644. A ring with 160 points per machine repairs that to about 17%. And I want to be honest about something, because it is often said the other way round. Even with 160 points, the ring is still less even than plain modulo was. What the ring actually buys you is that very few keys move when a machine joins or leaves. Now read the last column, because this is the point. The hot machine is at 96% in every single row. Virtual nodes fix the ring's own uneven arcs. The one hot key still resolves to exactly one machine. The ring was never about request rate. So what does work? 3 things, and here is the first one. Split the key. Instead of storing the value under one name, you store it under several. EVT:9001 #0 through #7. A read picks one of those 8 names at random. Different names give different hashes, which give different machines. Now read the write function underneath, because that is where the cost lives. One logical update is now 8 writes, and the value is stored 8 times in memory. And there is a surprise in the measurements. 2 copies took the hot machine from 96% down to 48.5%. 4 copies gave exactly the same 48.5%. No improvement at all, because 2 of those 4 copies happened to hash onto the same machine. 8 copies got it down to 25%. using 6 machines out of 8 copies. More copies is not the same thing as more machines. Here is the same diagram after splitting into 8. The one fat pipe has become 6 thinner ones because 2 pairs of copies collided onto the same machine. The busiest machine dropped from 96% to 25%. But look at the number that did not change. The cluster average is still 10.5%. Splitting a key moves work around. It never removes any. You spread the same 19,000 reads over more machines, and you pay for that with 8 times the writes and 8 copies of the value sitting in memory. The second fix is a small cache inside the application process itself, sitting in front of the cache tier. This is a TTL cache with room for 100 keys and a lifetime of 1 second. On a read, you look in the local dictionary first. If the value is there, you are done, in microseconds, with no network call at all. Only a miss crosses over to the cache tier. The effect is enormous. Just over 90% of all reads now never leave the application process. Machine 3 drops from 96% to 1.2%. The tier sees 40 reads a second for that key, instead of 19,000. Now the cost, and it is a real one. There are 40 application processes. Each one holds its own copy, and each one expires at its own moment. A change can take a full second to be visible everywhere, and half a second on average. You cannot clear them all at once. You traded freshness for evenness, and that is a decision, not a free win.
The third fix handles one specific moment, when the hotkey expires. Without it, the value disappears, and every request that arrives while you rebuild it goes straight to the database. At 19,000 reads a second, a rebuild that takes 200 milliseconds sends 3,800 identical queries to your database. If the rebuild takes 800 milliseconds, it is 15,200. That is called a stampede, and it is very often the thing that actually takes the site down, not the hot machine itself. Single flight fixes it. The first caller to miss starts the rebuild and puts a future into a dictionary. Everybody else finds that future and waits on the same one. When it finishes, they all get the same answer. 3,800 queries becomes 1. And notice that the number no longer depends on how slow the rebuild is.
Now let me be very clear about what does not work, because these are the things teams reach for first. More machines? No. More virtual nodes? No. A bigger machine everywhere? You pay 10 times over to fix one. More memory per machine? The problem was never memory. A different hash function? The new function still sends one key to one place. Another replica of the cache? That helps you survive a machine dying, not a machine being busy. Pinning the hotkey to its own machine by hand? You have just built a single point of failure and given it a nice name. Everything in that list treats the cluster. The cluster was never sick. One key is sick, and only the 3 fixes on the left touch the key. Last thing, how do you see this before your users do? First, stop charting the average. Chart the busiest machine. A maximum drawn next to a mean is the single most useful change you can make to a cache dashboard. Second, use the tools you already have. Redis can sample which keys are read most often. Memcached can report per key statistics. You do not have to guess which key it is. Third, here is a rule of thumb. If one machine is running at more than about twice the load of the median machine, you do not have a capacity problem. You have a hot key, and buying hardware will not touch it. The cluster average is the most comfortable number on your dashboard, and it is the one that lies to you. That is hotkeys. One key, one machine, and no amount of hardware. If this made the topic clear, a like genuinely helps. And subscribe if you want more system design explained the same way. Thank you for watching.